At CERN, scientists are eagerly awaiting potential breakthroughs from the world's largest and most powerful particle accelerator. The Large Hadron Collider, a testament to modern scientific innovation developed by the European Organization for Nuclear Research, has illuminated numerous enigmatic scientific phenomena. Recently, Brian Cox has raised the alarm by revealing an unexplained and troubling occurrence at CERN. During a test featuring unprecedented energy levels, the facility's scientists encountered an unexpected and potentially disconcerting phenomenon. This discovery raises questions about its implications for unlocking the universe's mysteries, including the possibility of miniature black holes. Additionally, researchers are intrigued by its connection to the Mandela Effect. Let's find out why this mystery has left even the most seasoned scientists at CERN puzzled. The discovery of the Higgs boson in 2012 stands out as one of the most significant achievements of the Large Hadron Collider. This elusive particle, responsible for imparting mass to other particles, confirmed the existence of the Higgs field and its crucial role in the mass-giving mechanism. This breakthrough marked a pivotal moment in the field of particle physics, reshaping our understanding of the fundamental building blocks of the universe. In recognition of their contributions, Francois Englert and Peter Higgs, who independently proposed the Higgs mechanism, were jointly awarded the Nobel Prize in Physics in 2013. On July 5, 2022, a milestone was reached as the LHC detector activated all subsystems, initiating the recording of high-energy collisions at an unprecedented energy level of 13.6 teravolts. This remarkable feat was made possible by the tireless efforts of the operators, who had labored tirelessly since the LHC's inception the previous April. Following more than 3 years of extensive upgrades and maintenance, the LHC was primed to operate at the record-breaking energy level for nearly 4 years, promising enhanced precision and increased potential for groundbreaking discoveries. However, upon activation, physicists observed anomalous phenomena that piqued their curiosity. Speculation arose that these anomalies could be attributed to magnetic monopoles, yet the existence of such entities remains unsubstantiated by empirical evidence. Nonetheless, theoretical frameworks, including the concept of quantized fields and the compact nature of the U-1 gauge group, have fueled the notion of unification. In 1974, physicists delved into the concept of unification, leading to the emergence of grand unified theories. These theories put forth predictions regarding the potential stability and decay of protons, the existence of novel super-heavy particles, and, as demonstrated by Gerard Hooft and Alexander Polyakov in the same year, the existence of magnetic monopoles. It is essential to acknowledge that we currently lack empirical evidence substantiating the relevance of grand unification theories in our universe. However, the exploration of this possibility remains a worthwhile endeavor. When evaluating theoretical concepts, one critical consideration is the presence of pathologies that could disrupt or undermine the universe's functionality. Upon the proposal of Hooft-Polyakov monopoles, a significant pathology, termed overclosing the universe, was identified. Magnetic monopoles offer a potential solution to the monopole problem, which arises from an excess of stuff in the universe, resulting from the introduction of a large number of previously massless particles with non-zero masses, or the sudden addition of numerous massive particles to the universe. Inflation, a process that expands the universe to a state resembling flatness and imparts uniform properties to all observable regions, presents a potential resolution to the monopole problem. This understanding traces back to 1980, a period marked by the convergence of interest in Hooft-Polyakov monopoles, grand unified theories, and early cosmic inflation models. Physicist Blas Cabrera, in 1981, devised a cryogenic experiment employing a coil of wire specifically crafted to hunt for magnetic monopoles. The crux lies in the interplay of magnetic monopoles, universe, grand unification, and inflation, where the universe's early stages are characterized by high energy levels, allowing the spontaneous creation of particle-antiparticle pairs governed by Einstein's equation E equals mc². Inflation, a process that expands the universe to a state akin to flatness, while imparting uniform characteristics to all observable regions, presents a potential resolution to the monopole predicament. This realization emerged from the intersection of interests in Hooft-Polyakov monopoles, grand unified theories, and early cosmic inflation models around 1980. Blas Cabrera's experiment in 1982 aimed to detect magnetic monopoles within the universe. The setup involved a coil comprising 8 loops. The rationale behind this design was rooted in the notion that if a magnetic monopole were to traverse the coil, it would elicit a distinct signal through electric induction. On February 14, 1982, Cabrera revisited the experiment and was taken aback by the results. The recorded data exhibited a solitary signal closely resembling what would be expected from a magnetic monopole, sparking considerable interest in the scientific community. This discovery prompted inquiries into inflation, the potential existence of magnetic monopoles, and whether the observed phenomenon was an unprecedented experimental anomaly, technical glitch, practical joke, or unexplained occurrence. Numerous subsequent experiments aimed to detect magnetic monopoles, many of which featured larger scales, longer durations, and increased coil loop counts. In recent years, magnetic monopoles have been a focal point of scientific discourse, with grand unification serving as a prominent theoretical framework. However, the veracity of the events surrounding 1982 remains shrouded in uncertainty due to the absence of conclusive evidence. The Large Hadron Collider serves as a critical instrument in investigating the possible existence of magnetic monopoles, capable of generating these elusive entities at exceedingly high energy levels. Furthermore, constraints on the maximum temperature attained during the hot Big Bang phase are established by observations of gravitational waves, which are theorized to have originated from inflationary processes. If grand unification holds relevance within our universe, it can only manifest at energy scales surpassing the aforementioned limit. This implies that if magnetic monopoles indeed exist, they must possess a significantly high rest mass, estimated to be on the order of 10^15 GeV or higher. Nearly 4 decades have elapsed since the emergence of an intriguing experimental clue hinting at the potential existence of magnetic monopoles. Researchers established that these monopoles cannot possess a mass less than 70 times that of a proton, marking the first robust constraint on their mass. Subsequent examinations revealed an intriguing phenomenon, a prolonged gap in Earth's magnetic field lasting 14 hours. This occurrence sparked speculation, with some suggesting that CERN's activities were creating a portal through which entities from another realm could traverse. Despite the simultaneous release of other peculiar news, experts assured the public that there was no cause for alarm. Nevertheless, they acknowledged that during the period when the magnetic field gap persisted, it allowed particularly potent solar winds to penetrate Earth's magnetic shield. The magnetic field, often overlooked outside of science classrooms, plays a vital role in the functioning of our planet. Not only does it guide navigation by maintaining the orientation of compass needles towards the north, but it also shields the ozone layer from the damaging effects of solar winds. Despite its infrequent mention, the magnetic field's significance to life cannot be overstated. According to NASA scientists, further investigation into solar winds is necessary due to their potential to harm or disable satellites in Earth's orbit and cause power disruptions affecting entire cities. But what gives rise to this essential shield? It originates from natural forces and involves a rare occurrence from our neighboring star, the Sun, known as a co-rotating interaction region, CIR. When fast and slow streams of solar wind intersect in the low and middle latitudes of the heliosphere, they generate these CIRs, resembling celestial tapestries. Picture the heliosphere as a cosmic stage where spectacular performances unfold. The Sun's magnetic field and solar winds transform it into a theater, with coronal mass ejections gracefully propelled by the dynamics of co-rotating interaction regions. In the realm of magnetic phenomena, a notable occurrence took place in the early hours of July 7, triggering a prolonged G1 geomagnetic storm as reported by the National Oceanic and Atmospheric Administration. Deep within the solar wind, a complex narrative unfolded. A coronal mass ejection nestled within the stream just preceding the co-rotating interaction region. The question arises, should we be concerned about this fissure? Experts reassure that cracks in the Earth's magnetic field are not cause for alarm. Rather, they serve as our shield, safeguarding against the sun's turbulent outbursts. Initially believed to be transient, recent observations reveal that these fissures persist for extended periods, remaining open for hours at a time. However, amidst the myriad enigmas of the cosmos, a puzzle has emerged, capturing NASA's attention. Yet, a robust magnetic field now exhibits indications of an anomaly. The diminishing strength of its magnetic field raises concerns, indicating an anomaly scientists struggle to explain. Despite expectations based on stellar observations, the magnetism of this celestial body appears weaker than anticipated. This peculiar phenomenon, known as the South Atlantic paradox, has wide-ranging implications felt across a vast expanse, from South America to Southwest Africa. NASA coordinates a fleet of satellites and spacecraft, strategically positioned in orbits that complement one another, extending humanity's reach beyond Earth's confines. However, the weakening magnetic field poses a cause for concern, as it compromises our defenses against the sun's charged particles. This vulnerability underscores the delicate balance between our existence and the cosmic forces that surround us, emphasizing the intricacies of our relationship with space. While uncertainties linger, there is currently no immediate cause for alarm. Nonetheless, the implications of this enigmatic phenomenon warrant continued exploration and understanding. As we conclude, we invite you to share your perspectives, hypotheses, and encounters in the comments section below. Don't forget to subscribe and activate the notification bell to stay informed about the latest discoveries and developments in our exploration of the cosmos.